And next, I'm gonna introduce Jonathan Hurst, professor in Oregon State University. But I think today the role that he will speak about on is as co-founder of Agility Robotics. Jonathan, off you go. If you can share your screen, it would be amazing. And try to optimize for videos so that we see the full. Okay, great. It looks good. Off you go.
Okay, optimize for video. That will make the text all fuzzy, but that's okay.
That's okay, because usually we have problem with videos today, so it's better to see the videos rather than the text in good quality. Thanks a lot.
Yeah, apparently you can hear me okay, so everything's good.
Yes, everything is good from our side.
Excellent. So yeah, I'm talking about Agility Robotics. I'm sprinkling in a bunch of other things as well. What we're doing is aiming to build robots for a human world. This is really our mission, just to kind of set the stage. We want our robots to operate in our spaces. We don't want to have to engineer and design infrastructure around enabling robots to do work. We want robots to seamlessly move in spaces designed for us and be able to work with us. I think a lot of people are inspired by this very same goal. I want robots helping me in my home and my business, and I'm really excited to be working on that kind of thing. So this talk is really, I saw a lot of parallels when I was watching Alke's talk earlier today, thinking about kind of the hierarchy. And he was talking about reflexes in passive dynamics and the different layers of the brain and cycles and clock cycles. But the same thing is just sort of inherently true. It's not something that we have to design or think about or engineer. It's something that we more or less are discovering. Certain things just happen at very high control rates. When you have an impact with the ground, it's only inertias and springs that really matter. But then, of course, at the very, very slow control rates, then you're thinking about where you're going to go in a space. And then, closer to like 30 Hertz, you're thinking about where you're going to place your feet. It's not really useful to plan that much faster because you only get to so much in terms of a stride frequency. You only get to place your feet once per step. But you have to do that planning then through the whole dynamics of the rest of your system. So it's really important, and making these robots function, it's all about designing your behavior at a high level. What is it you even want to do? And then you have to really integrate this whole control hierarchy. Just an example of it is you have, a spring mass kind of dynamic behavior, but then you also have a footstep planner, and the two are going to contradict. Where you want to place your feet, maybe on a stepping stone, is different from where your balance needs to place its foot in order to stay balanced. So that's why you really have to plan ahead. You have to be looking forward. You have to have a bit of a model predictive control conceptually going on and things like that. So this talk kind of goes through a little bit of starting at the dynamics foundation, which is where we've started in our research and then in our implementations, and then working our way up, building kind of this foundation, starting with this foundation in dynamics and building it up brick by brick. So progress over the years. There's robots before this, but starting with Atrius, it was very much about science and what is legged locomotion, and can we even capture the physics, and what are the physics of walking and running. And I think that we kind of understand some of those core science pieces at this point from the biomechanics community, and then from people demonstrating and showing these things on robots. And so now it's really transitioning into more of an engineering challenge, an engineering problem. But we really think of this as like engineering with a science attitude, right? We're kind of discovering engineering solutions more than we are creating them so much. And everything we do on the robot has to have a first principles foundation. Like the change in configuration from Atrius to Cassie in the shape of the leg had to do with antagonistic work and motors working against each other, and how do you eliminate that and have all the motors working for your task in a walking gait. Adding the degrees of freedom in the feet and the shape of the torso and where the arms go on the robot. All of that has been based on first principles, capabilities we're trying to achieve, and really thinking about this from engineering with a science attitude. Now, I also want to say, though, that the control that's underneath all of this is at least as big of a challenge and as big of an engineering project as designing the hardware. And it's growing. It's actually going to be a much bigger part of Agility Robotics is the software team. The hardware is quite capable. The software really makes it happen. Okay, so a little bit of history. Here's Monica Daly and Andrew Biemener's work. Guinea fowl being surprised by tissue paper by a hole in the ground. That tissue paper hides this hole in the ground and the bird can just sort of keep going right on through it. And so this kind of obviously dynamic basis where there's no planning, there's no perception, it's just the dynamical behavior is robust to those kinds of disturbances. That's really the inspiration for Atrius as a science demonstrator, which also has no perception, has no planning, has some basic heuristic controllers, but is capturing the core physics of legged locomotion. And obviously the morphology is different, right? So it's the capturing the same physics, and we're showing that with this obstacle here that's just being thrown in the way, just like it was with that bird. And we're getting performance that is, you know, close to human level performance or exceeds human level performance. If you imagine yourself blindfolded and your arms, you know, wrapped around your body, and someone says, walk forward confidently. The ground may or may not be rough. I'm not telling you what's there. You know, we found we could do, oh, and you're not allowed to use your feet. You have to walk on like little point feet, right? We found that people could really only do about what Atrius could do at the time. Now, of course, Atrius cannot stand, it cannot steer, it cannot plan its way through the world. There's a lot it can't do. This was a really nice science demonstrator and the beginning of the kind of the foundations. And here I'm showing, you know, a similar behavior with Digit. This is our most recent robot at Agility Robotics, and we can pretty much take it outside and go where we want. In this case, I don't know if the perception is being used or on. I don't think so, but you know, we can handle various terrains just kind of using the dynamics of the machine itself. When it's swinging its arms, that's just about inertial actuation. It's not something that is puppeteered or made to look a certain way. Okay, and now here's the Cassie robot. This is running actually a learned policy that's generated through machine learning. And this is part of a 5K that we just recently ran, a full 5K on campus at Oregon State. We're still working on editing together the video to show that whole 5K and tell that story, but here's a clip from it. Again, there's no perception here. This is all a dynamical system. We're able to utilize a bit more of the dynamics of the hardware because we're using a learned policy rather than a reduced order model-based policy here. But it's still at kind of that second level up in the control hierarchy where there is no planning and there is no perception and there is no ability to decide whether to place the feet high or low or, you know, where to place the foot other than by the balance control. And that kind of, this is what's really amazing, is that kind of approach where we actually don't have any perception, we're not thinking about the world, and it's purely the low-level dynamics, can be really, really robust. It can even go up and down stairs. In this video, Digit or Cassie has no idea with every step. It doesn't know if the next step is going to be flat ground or a step up or a step down. There's no information and there's really no planning going on. This is just training a system to be using its dynamics to be robust in the presence of some pretty large disturbances. Now you imagine we can use this, but then also add on top of this as part of the control hierarchy, perception and planning through the dynamics and actually choose where to place your feet. What that means then is if you miss a step, you're still going to be able to rely on this level of robustness. But for most of you, but this gait is fairly stompy, for example. So when we don't know what's in front of us and have no idea, it's lifting its feet up really, really high and bringing them down pretty fast to make sure it gets its foot onto the ground, regardless of how high the ground is. And, you know, so that's not ideal for a lot of behaviors and a lot of gaits. We're going to want to plan our gait, but still have a lot of robustness if we do make mistakes in our planning and our perception. So, you know, this point is just to show how you might start to think about doing that. We have a simple spring mass model here, very simple. and just an actuation in terms of adding energy to the leg length once during the center of stance, and placing your foot. Those are the only two control inputs you have. And we only get to look ahead 2 steps. So that's the only thing that this simulated robot knows about the world, is 2 steps ahead. And then it's a really simple kind of decision tree. It's a Monte Carlo planner, just to test out the concept of how do we plan through a world and don't argue with the dynamics, but instead the interface is to the low-level dynamics. So we're not, we're not arguing with the low-level dynamics. We're utilizing the dynamics and the robustness that we could have with the dynamics, but we are communicating to the system in a way that, like stride length and energy insertion, but not the low-level torques or forces. And this, at least in a planar system, with just a few weeks of simulation work, very quickly was able to go up and down stairs and handle all kinds of different obstacles. So in concept, this is what we'd like to be doing then with Digit and Cassie and physical real robots. And so here's a very, very beginning of that, is we're giving it a tiny bit of information. We are only telling it general slope of the space in front of it. And it's just dynamics and balance in terms of where it places its foot, but it at least knows approximately what's the slope of the hill right there. And you can see, I mean, there's a lot there with the legs sort of slipping around and moving, and it's a very uneven ground, and that's just the dynamics have to deal with that level of uncertainty. The planner couldn't anyway. But we know that the slope of the hill, and that increased the robustness of the behavior quite a bit. Otherwise, it would basically be stubbing its toes the whole way up. Okay, now here we're adding just a little bit more information. There are depth cameras underneath the robot and on the front of the robot here. And so Digit has kind of a depth map locally of what's around it and can see obstacles like these 2x4s that are on the floor. And then just modify the gait a little bit so you don't trip on them. Now, if we did, we'd be fine. The robot can step on those and recover with just the dynamics, but still, generally, you'd rather not have to rely on that. You'd prefer to step around and over things. And you can actually, in that last one right there, I'll back up just a little bit, you can see that it did overshoot a bit. It had a plan, and the plan wasn't perfect, so now the dynamics are what caught the balance and kept it from falling. And then when you kind of incorporate and you're just walking around the world, this was really very pleasantly surprising to me when we did this. It incorporates pretty well, and it starts to just look easy. It's like no big deal. We're just walking around and going up and down the curbs, but for a lot of years, this was a really challenging thing to figure out how to do. I hope a lot of solutions in legged locomotion are going to be like that, where they seem really hard, and in the end, it looks easier than it was. Now that extends to manipulation as well. And here in this video, I'm showing on the right kind of what the robot sees and perceives. And you'll note that it's not perfect in terms of what's really happening and where it really is. And what Digit's just trying to do here is always get the box back to a particular location. And Taylor, one of our engineers there, is moving it around and kind of messing with the robot, and Digit's trying to choose then how to get it back to where it needs to be. With very limited, oh, and see, there's a disturbance where the planning and the perception was wrong, and the robot was able to easily deal with that without replanning, but just the dynamics at the base. Okay. And we're starting to stack these things together to do some useful applications. There's a lot of different companies that use kind of these totes, and you do bin picking and place things in the totes, and then pick the totes up off of a conveyor belt and carry it over to a shelf, or pick it up off the shelf and put it on a cart. I don't know, a lot of these jobs are very automation resistant because of the manipulation challenge. And having a robot like this with the full body kind of control, the full body manipulation, Digit can squat all the way down, pick up a package off the ground, lift it up to a shelf that's 6 feet high and set it on the shelf overhead, or vice versa. And the kinds of tasks where all of the interest and all of the creativity and all the judgment have already been stripped out of it, and it's a very repetitive kind of put things here, put things there kind of job. The only reason it hasn't been automated is because of the manipulation challenge. That's kind of the ideal place for Digit to just walk in and start doing those things. And that's what we're doing with a couple of different large logistics customers right now. And this is a real video, just to show from something like 6 or 9 months ago. This was at the height of the beginning of the pandemic and wildfires in Oregon. It was an interesting time. We stayed indoors a lot, but 20-pound box and lifting it off a shelf. So Digit knows vaguely the location in a room of where that box is. So there's kind of the high-level planning, which is very, very simple. Because we can specify that for most of these roles and most of these tasks. But Digit is making the decisions. Once it sees the fiducials, it knows the location of the box, or once it sees the fiducial in the box, it can see the box. And just decide how it's going to grasp it specifically, and then plan its own path through the room and set it down in another location. I guess another comment about the Dynamics Foundation too is not just being robust to differences in the ground surface, but when you pick up a 20-pound box versus not having anything, being able to transition conveniently when it picks things up and sets them down is important. Actually, watch the ankles a little bit when it sets the box down. You can see the center of pressure changes abruptly when it drops the box and has to correct for that really quickly. So we're building up to this. We're building up to robots doing a bunch of different tasks: unload a trailer, deliver packages to the front door from an autonomous vehicle, pick up boxes from the backroom shelves, and then, not shown here, really the more common ones, which is the repetitive picking things off of a shelf and placing it on a conveyor belt or depalletizing or things like that. That's kind of early applications where it's a controlled environment, and I think these robots can start to be useful in the real world, like really, really soon, and then gradually improve the intelligence, the human interaction, and start to become useful in our homes. And I think I'll stop there. I think I went reasonably quickly and kind of on purpose, and I wanted to leave time for questions.
Yeah, thanks a lot, Jonathan. Please, everybody, ask questions either by raising your hand or by typing in the chat. One quick question I have while we're waiting for people. In the logistics, do you see, basically, do you think that legged systems are really required compared to mobile platforms, for instance, and in which cases, basically?
Yeah. Oh, even better. So we're not going to replace forklifts. We're not going to replace the wheeled autonomous mobile robots. We're not going to replace the, Kiva Systems, now Amazon Robotics kinds of solutions for moving shelves around. Really what the legs are useful for is sifting into a human location where there's stairs and curbs, or you're going in and out of the tractor trailer and there's obstacles on the ground. There's a gap between the truck and the loading bay, and then the truck is sometimes high, sometimes low, sometimes a gap there. It's also the ability to have the whole body manipulation, like I mentioned, being able to bend way down, pick something up off the floor, lift way up and pick up something overhead. It's also the ability to have a very narrow form factor in order to be able to do these things. The robot can go wherever people go and hallways and things like that while still reaching up very high. You have to be dynamically balancing all the time in order to do that. And feet allow you to be completely non-holonomic, meaning you can rotate or you can move left or right or forward or backward at any point in time. And you don't have to, do the backing up a car 5-point turn kind of stuff. But that exists in the vertical direction and everywhere else as well. So think of the legs more as the ability, not just the mobility solution, but a big major part of the whole of the manipulation. It's 24 degrees of freedom as a manipulator. Think of it as that way, rather than thinking of it as a mobile base plus, 2 5-degree of freedom arms. It's a 24 degree of freedom mobile manipulator.
Right. Thanks a lot. Marco?
Yes, I have a question regarding the newest version of your robot. What will change with the version 4? I saw, obviously you can see the head with probably it's a new sensor with cameras.
Yeah. So there are, let's see, there we are. There are a few key features. So it's just a rendering on the right. It's in progress now. The first revs are headed out to the machine shop now. We're adding the head for a couple reasons. Number one, we need some sensors up there. Number two, we really need to be able to interact with people well and give it cues so that people understand what the robot is about to do, so that the robot doesn't surprise people when it starts to move. I think that the interaction with people and making sure that people like the robot, and while they are safe around the robot, it will be certified, but they also feel safe. They also feel comfortable around the robot. And so the industrial design and how the body and the arms and everything is shaped, the colors, the size, and then also the cues that it gives you, which kind of need a head. And also, we can't land in the uncanny valley. If you look at maybe the digit V2 or the digit V1, you might say, oh, it's missing a head. And that's just because it's humanoid. And so you have certain expectations of it. Fortunately, it all kind of comes into place. It's really a natural place to give cues, is with a simple set of eyes like that. Okay, so a head for HRI for added sensors. Also the 5G, 4G, and Wi-Fi antenna going up there is the best place for it. We're also adding self-charging docks. So the robot walks up to the dock, sits down, and charges itself. We are paying a lot of attention to the manipulators. Right now, this is kind of like, a pincher grasp with your thumb and forefinger, but larger scale. And you can do a lot with a pincher grasp like that. But in order to control the pitch of a box, once you've fixed it up, we need at least 1 or 2 additional degrees of freedom in the manipulator at the end. So we're putting a lot of time and effort and thought into kind of first principles, not reproducing a human hand, but we want to be able to open doors, catch the robot when it falls, manipulate boxes and things like that. And what do the manipulators look like? And then finally, I would say we're really thinking about feet a lot. There's been a lot of thinking going into the leg configuration as we continue to build and grow. Physical springs are there right now to basically mitigate the impacts of the feet on the ground, yet it's still a little bit stompy. And that's a problem for durability of the robot. It's inherent because you have reflected inertia from your actuators, and that's always going to exist. And it's something that is going to be a problem if there's 1,000 robots in a warehouse and they're all making these sort of loud noises when they walk around. It's kind of unacceptable. So for all those reasons, we've really started to a research push over the last 2 years to understand how to mitigate the impacts with a foot and how to understand how a foot would work from first principles, not trying to copy an animal directly, but maybe be inspired by them. Maybe move some of that compliant behavior from up higher on the leg down into the foot at the very end effector of the device, so that it isolates all of the inertia during an impact.
Thanks a lot, Jonathan. Actually, there are so many questions in the chat. We will not be able to handle everything. One comment is, I just noticed that you use the leader as neck. It's first time I see that in a humanoid. It's very nice. Maybe I can ask you one more question. Do you think that locomotion on regular flat terrains has been solved basically for Cassie or Digit, and now the challenge is in non-regular terrains or unexpected terrains?
I think that general legged locomotion and manipulation and robots like this are going to be improving for 100 years. I don't want to say it's solved, but I do want to say that yeah, more or less, we know how to walk around and the dynamic behavior and the dynamic robustness that you could see. We know how to do that, and we're confident in how to do it. And there's still a lot of going from, we demonstrated it and we showed that, to it is a completely well-engineered industrial product. There's a hard path there with a lot of engineering. And then yeah, the question is going from that point of you've got basic dynamics that can trip and recover to you're planning your path through a boulder field. Yeah, that's still there's a lot of progress being made in that area, and there will continue to be for some time.
All right, cool. Maybe a last question, and please try to answer everything in the chat. We're gonna share the chat also in the post media material. Let me see if there is. Basically, one question is if you are using reinforcement learning in your for your controller, basically in Digit.
Yeah. Yes, we are. And really, it's a matter of how much and where. So the video of Cassie going up the stairs was a black box learned policy that was just put on the robot. And it was the stair climbing policy, and we switched with the controller to the stair climbing policy and then gave it a velocity to go up the stairs. With Digit, we can't do that. You really need to have this whole body control, for one, which is a hard thing to learn for all the different behaviors you want. It's just the dimensionality gets too big. And so you need all of the traditional engineering approaches, you know, the reduced order models, the QP optimizers, the model-based control, and then you insert learning into little pieces and places of it to get into the corners of the dynamics and to really improve the behaviors.
All right, cool. I mean, I have to say that I think you gave a talk on this topic, and it should be in the Agility Robotics YouTube channel. So
yeah, that's true.
The audience probably should go and watch this. It's a really nice talk. I think with this, I would like to finish the session. Thanks a lot, Jonathan, again. And please answer. There are like 20 questions now appeared in the chat. So I mean, maybe in the next workshop that we invite you, you have to speak 5 minutes, and then we go with questions. I think that's the idea. Okay, cool. I'm gonna hand it to